In this short video segment, I will talk about stability of legged robots and in particular about dynamic stability of legged robots. As we have seen in the control section, there is two distinctly different ways of how legged systems are moving. On one side, statically stable gates, which means that there is multiple points that are in ground contact, which span a support polygon, and the center of gravity, the projection of the center of gravity on this support polygon means that it lies within the support polygon. If this is the case, then this robot is statically stable, so you can block all the joints and the system will just stand there forever. In contrast thereto, dynamic gates, which is in fact like most of the gates that humans or animals are using, means that the system is statically unstable. So if you would block all the joints, it would just fall down. For a legged system, that means we have probably only points in contact, maybe very small support polygons or support lines, as in this example of a trotting gait, and the robot has to continuously step in order to balance it. Now, if you analyze stability for this case, we cannot analyze stability at one instant in time. Instead, what we have to do is we have to do a so-called limit cycle analysis. So we have to look at dynamic gates on a step-to-step basis and see whether or not the system can stay on a stable limit cycle. We can look at this in the example of this single-legged hopper. This is like one point contact, and obviously this system can only be dynamically stabilized. If you would turn down the motors or block the motors, the system would just fall over. Now, if you analyze stability for that, what we have to do is the following. So what we're looking at is at the time evolution of this hopper, and we have here an example of a hopper that lives in 2D plane. And what we're interested in is how the behavior looks like from one single apex to the next one. An apex is the highest point in the flight curve, so we're looking at what happens from that point to the next point. And to analyze this, we're looking at the complete state space. So we have velocity in x, velocity in y, and the height. And we're looking at how the state evolves in this time. So you have here the complete phase graph. You see here a small transition, which is due to the impact collisions that we're having. So we have a discrete jump in the velocity. And now, since we're analyzing the apex, so the highest point in the curve, we're cutting this complete plot, and we're analyzing at that point where the velocity in vertical direction is 0. And as we can see, this nominal limit cycle always passes through the exact same point. Now the question is, if you have the nominal limit cycle, but then you disturb the system, you get an offset. And the question is, how does that offset evolve over time? So does it eventually diverge from this nominal point that it should go through, or will it eventually come back? So what we're looking at is a so-called Poincare map. So the mapping of the state at transition k to the state at transition k+1. And as we know, we have a fixed point. That means on this limit cycle, I'm passing through this fixed point, and if I'm doing this Poincare mapping, I will again come back to the exact same fixed point. Now, what we have to look at is how does this thing evolve over time. So we're linearizing this mapping. We are taking this dp after dx, which means we get a linearized mapping of an error in xk to the error in xk+1. And we have to see how does that evolve over time. So what we have to do is we have to make an eigenvalue analysis of this linearized mapping. And if all the eigenvalues are smaller or equal to 1, then this thing is stable. So it will eventually come back to this nominal point. If 1 is larger, then this will diverge and the system is unstable. This effect of stable limit cycle is what people have been using to build passive dynamic walkers. So what you see here on the left is a system that has not a single actuator, but it's still able to walk stably on a treadmill. If there's slight disturbances, it will compensate these disturbances, it will automatically come back to this stable limit cycle. Interestingly also, this system, if you look at it carefully, it moves almost exactly the same way as a human is moving on a treadmill. So that means this passive and also stable limit cycles is also something that drives human and animal locomotion to a large extent. A side element that is interesting here for you to understand is that since this system has not a single actuator included, that means that the only energy that it has or that is introduced to the system is due to the slope that it's walking on. So in other words, if you calculate the cost of transport, which is the energy that the system is using in order to travel a certain distance normalized with gravity, so this cost of transport is a unitless measure, then this is nothing else than the slope that the system is walking on. So the more efficient we are, the less of a slope we need in order to make such a robot or passive system walk. Now in the normal case, locomotion doesn't have to be not necessarily stable. So that means you have a limit cycle. If you disturb it too much, the system will diverge from that limit cycle and then eventually fall over. It's actually the case for any limit cycle, even if it's stable. If you disturb it hard enough, it's gonna be off. So the linearization is only valid in certain area around the limit cycle and it will fall over. In order to make these systems walk stably, what we have is we have to introduce a foot stepping controller, which essentially, depending on how the system is moving and how the system is disturbed, figures out how far away it has to step. And if you do that, you all of a sudden becoming stable. So even if there's large disturbances that are beyond what the stability of the nominal limit cycle can compensate for, you can compensate for external disturbance pretty well by making longer or shorter steps. Now this foot placement is exactly what is used in order to stabilize the single-legged hopper that we started this video segment with, and it's also the same controller that is used that we're in order to stabilize, for example, a quadrupedal robot. And I will present you in the next lecture a lot more details in how we're getting to a robust dynamic behavior for a quadrupedal system like this animal robot that we see here on the right. With this, we are at the end of this lecture, and thank you very much for your attention.